Assalamualaikum warahmatullahi wabarakatuh and hello everyone. We are Group 8 and today we will present our topic radioactive pollution. In this presentation, we will explain the definition, sources, facts, health effects, case studies, safety measures, and conclusion related to radioactive pollution. My name is Nur alias SAFIYA binti MOHAMMAD HAZUAN, metric number 8211552. Now, I will explain the definition of radioactive itself and radioactive pollution. Radioactive refers to unstable materials that release energy during radioactive decay. This energy is emitted as ionizing radiation such as alpha, beta, or gamma radiation. Radioactive pollution means the unwanted release of radioactive substances into the air, water, soil, or organisms. It becomes harmful when humans or ecosystems are exposed to radiation through inhalation, ingestion, or food chains. The key point is that ionizing radiation can damage cells, tissues, and DNA. Moving on to the sources of radioactive pollution, it can come from two main sources, which are natural sources and human-made sources. For natural sources, radioactive pollution can come from radon gas from rocks and soil, uranium and other radionuclides in rocks, soil, and water, and also cosmic radiation from space. For human-made sources, it can come from nuclear power plants and nuclear accidents, medical radioisotopes and X-ray equipment, industrial and research applications, as well as radioactive waste and nuclear weapons testing. So, radioactive pollution is not only caused by human activities, but it can also occur naturally in the environment.
So next slide is about facts about radioactive materials. So now I will explain three important facts about radioactive material. So the first fact is that radioactive material emit ionizing radiation because they have a unstable atomic nuclei. To weaken the stable, they will release energy in the form of alpha, beta, or gamma radiation through a process called radioactive decay. And then the second fact is that each radioactive material has a different half-life, which is the time needed for half of radioactive substance to decay. For example, iodine-131 has a half-life of only 8 days, while cesium-137 lasts about 30 years. So the longer the half-life, the longer it remains in the environment. So lastly, radioactive material can come from both natural and human-made resources. Okay, natural sources include uranium in rocks and radon gas from soil, while human-made sources include nuclear power plants, medical equipment, and industrial application. So now let's look about bioaccumulation and biomagnification. Let's look at how radioactive material move through the environment. So bioaccumulation is the gradual build-up of radioactive substance inside a single organism because they are absorbed faster than they can be removed. For example, cesium-137 accumulates in muscle, strontium-90 in the bones, and iodine-131 in the thyroid gland. So the next one is biomagnification. On the other hand, happens through the food chains. So radioactive substance move from plankton to small fish, then to larger fish, and finally to humans. At each trophic level, the concentration become higher. So the good example is that Fukushima nuclear accident, where radioactive cesium entered the ocean, accumulated in the marine organism, and eventually reached humans through seafood consumption. And finally, let's discuss about health effects of radioactive materials. So, high dose of radiation over a short period can cause acute effects, such as nausea, vomit, fatigue, skin burns, and hair loss. In severe cases, it also can lead to acute radiation syndrome, or we call it as ARS. Meanwhile, the long-term exposure increases the risk of serious disease, including the cancer, leukemia, thyroid disease, infertility, and genetic mutation. This happens because ionizing radiation can damage the DNA inside our cell, which may lead to mutations or uncontrolled cell growth. So one well-known example is the Chernobyl accident, where children developed thyroid cancer after consuming or contaminated with iodine-131. Okay, another example is radon gas, a naturally occurring radioactive gas that can increase the risk of lung cancer after a long-term exposure. So overall, these examples show why proper radiation safety and environmental monitoring are very important.
Hello everyone, I'm JUNJIE. Now I will talk about why we use radioactive materials. Our example is cesium-137. Although radioactive materials can be dangerous, they are very useful when they are used safely. In medicine, cesium-137 is used to help treat cancer. It is also used to sterilize medicine equipped. In industry, it helps measure the thickness of purple and matter. It can also detect leaks in purple lights. Scientists use radioactive materials for research and environmental studies. In agriculture, radiation is used for food irradiation. It helps reduce bacteria and keeps food fresh for a longer time. Next, I will talk about the radiation warning symbol and the monitoring of radioactive pollution. First, the radiation warning symbol warns people that radioactive materials or radiation may be present. When people see this symbol, they should be careful and follow safety rules. Next, radioactive pollution needs to be monitored regularly. One control is the higher content. It is used to measure radiation levels. Scientists also test the air, water, and the soil to check for radioactive pollution. In addition, the government monitors radiation to help protect people and the environmental. Now I will pass the next.
So now I'm going to be talking about our first case study, which is the Chernobyl incident. So on April 26, 1986, in Chernobyl nuclear power plant in Soviet Ukraine, they experienced a catastrophic event during a system test. So this event is considered as the worst nuclear disaster ever happened in history. So how did this incident happen? A low power engineering experiment triggered a critical power surge during a system test in the power plant, and this produces a steam explosion that completely blew the reactor core apart. So when the uncontained reactor core was blew apart, it releases various pollutants that were radioactive materials, and some of these pollutants were iodine 131 and cesium 137. These pollutants have 8-day half-life and a 30-year half-life respectively. These pollutants were volatile gas, meaning they pollute the atmosphere without causing any visible change in the air. And also the radioactive element of strontium-90 isotope, it causes a heavy rain of radioactive heavy rain in the local areas. So from this incident, it became a very costly nuclear disaster, and actually the costliest nuclear disaster ever in history. It was rated a maximum level 7 by the International Nuclear Event Scale. This was caused by a lack of secondary concrete containment structure in the power plant. Next, let's look at our second case study, which is about the Fukushima incident. So the 2011 Fukushima incident was also a catastrophic nuclear accident that happened in the city of Fukushima inside its nuclear power plant in Japan. So unlike the Chernobyl incident, which was caused by human mistake, the Fukushima incident was caused by a natural earthquake and also a following tsunami that came after the earthquake. So this was considered as the second worst nuclear disaster ever after the Chernobyl incident. So how did the incident happen exactly? The magnitude 9.0 earthquake destroyed the city's power grid, and afterwards it also followed a 14-meter tsunami that flooded the backup generators that were powering the cooling system of the power plant. So when the generators of the power plant were completely flooded, the station blacked out, and it causes the reactor core cooling system to fail, and the reactor core rapidly increased in temperature until it eventually broke apart. The core eventually meltdowns and forced the workers to be contaminated, the workers to be exposed to the volatile gases of iodine 131 and cesium 137. These gases were radioactive, contain radioactive characteristics, and it causes the workers to fall sick afterwards, and many of them unfortunately passed away. Meanwhile, the seawater that flooded the cooling system created millions of tons of wastewater that was polluted by cesium 134 and tritium aka hydrogen 3. So these pollutants caused massive contaminated water to flood the city. So from this incident, they learned to create a structure that can safely contain heavy elements such as plutonium and liquid isotope. The installation of advanced liquid processing system to treat water before precipitate discharge was created as well. And from this incident, they learned to take precaution as much as possible, so that and if another earthquake or tsunami happen, this massive disaster could be prevented.
Thank you, Danny. Now let's look at how we detect radiation and what measures we take to control it. The Geiger-Müller counter is our most common tool for detecting radiation in the field. Inside the tube, there's a gas. When radiation enters, it knocks electrons off the gas atoms, creating charged particles. A high-voltage electric field multiplies this into a large pulse. We call this an avalanche. This pulse becomes the clicking sound you hear. A special gas inside also helps the tube recite very quickly, ready for the next particle. Readings are shown as counts per minute or calibrated to microsievert per hour. For context, normal background radiation is about 0.05 to 0.2 microsievert per hour. However, it has limitations. It cannot tell different radioactive materials apart. It counts everything equally. It cannot distinguish cesium from iodine. For that, we need more advanced instruments. Also, at very high radiation levels, the counter can get overwhelmed and miss particles during its short recovery time. Despite these limits, it remains essential for rapid emergency screening. After Fukushima, hundreds were developed to map contaminated zones in real time. It's fast, portable, and give us immediate answers. Once we detect radiation, how do we control it and protect the people? There are 3 golden rules: time, distance, and shielding. First, time. Your total dose equals dose rate multiplied by time. So if you cut exposure time in half, you cut your dose in half. At Chernobyl, workers in the most dangerous areas were rotated every 5 to 15 minutes. Second, distance. Radiation drops off quickly. Double your distance and you get only a quarter of the dose. That's why we use robotic arms and long tools to handle radioactive materials from far away. Third, shielding. Gamma radiation requires dense materials like lead, concrete, or water. Engineers calculate the half-value layer, the thickness needed to reduce radiation by half. For environmental cleanup, we use vitrification, melting liquid waste into solid glass blocks that traps radioactive atoms inside, stable for thousands of years. We also use sunflower to absorb cesium from soil through their roots. We harvest and burn them, reducing waste volume by about 90%. Finally, all this follows the ALEEYA principle, as low as reasonably achievable. The public dose limit is 1 millisievert per year. These standards guide every decontamination effort, from Chernobyl to Fukushima.
In conclusion, radioactive pollution can contaminate air, water, soil, and living organisms. Ionizing radiation may cause health effects such as cancer, genetic mutations, and radiation sickness, according to WHO. Radioactive materials are useful in medicine, energy, industry, and research, but they must be handled safely. Therefore, proper waste disposal, shielding, PPE, monitoring, and policy enforcement are important to reduce risks. Overall, radioactive materials can be beneficial, but only when they are managed properly and safely. This slide shows the references used in our presentation. That is all from our group presentation on radioactive pollution. Thank you for listening and giving your attention.